Hi, everyone. So I want to continue in the same vein as Raf and remark that we do live in extraordinary times. And in fact, today teachers connect with students and doctors connect with patients that are thousands of miles away. We have robots that do pack products on the factory floor. We have 3D printing that creates customized goods. We have network sensors that monitor facilities. We are surrounded by a world of opportunities, and these opportunities are only going to grow larger as we consider the impact of AI and robotics on our physical and cognitive work. So just picture this. Picture a world where routine tasks are taken off your plates. Garbage bins take themselves out and they disappear, supported by automated infrastructure. Vegetables and fruits show up at your doorsteps, delivered by drones. And intelligent assistants, whether embodied or not, help you optimize your life to work better and to live well. It is extraordinary to think about how we would live in such a world. And much of this progress is actually enabled by our advancements in robotics. Now, when we think about robots, it's important to think about the machine as having a body, hardware. This impacts what the machine will be able to do. And the brain, or software, this impacts how the machine will be able to control its body to achieve the task. And it requires great reliability, as Raf just told you. Now, at MIT, we are very excited in developing the science of autonomy, and in doing that, we want to improve the machine brains, the machine bodies, and the interactions between machines and people. So I want to give you a few examples for each of these three directions. So, machine brains. I will use an example from autonomous driving. We've been working on autonomous driving for many years before it was a thing. And this is one of our autonomous vehicles. It's a Toyota car extended with sensors and with computers. And in our initial work, much like every other company in the space, the computational pipeline for an autonomous car goes a little bit like this. You have sensors. The sensors look at the world. Through some reasoning, the sensors determine where are the obstacles, where the car is located relative to everything else in the world, where the car is in the map. And then the system figures out where the car should go and proceeds to execute that maneuver. So this is the general recipe that all car companies are applying. Now, the problem with this pipeline is that absolutely every case in the physical world is actually finely tuned in the solution. And there are many situations for which the solutions do not work. So if you have rainy weather, or there are no lane markings, or it's nighttime driving, if you want your robot car to deal with these conditions, you'd have to write some special code. So the question we're wondering is whether it is possible to eliminate that parameter tuning that goes inside the brain of a car, and to learn directly from humans how humans drive. And this would not require any hand-made parameters. And so in our project, we are looking at whether it is possible to learn from a single camera image how the car should steer. And the answer we've come up with is yes. And here you can see an example of a robot car that is driving for the first time on a road, whereas in fact the car was trained in the city in very different environments. And in blue and in red, you see ground truth and what the car should be doing. And it's kind of exciting. This car is driving at 25 miles an hour. And if I think about my own first ride, it was not this smooth. So using this, the latest ideas in machine learning, we can improve the brains of machines. Now, using the same type of strategy, we can also tackle other problems in robotics. For example, we can tackle robot manipulation, and we might even ask how many robots does it take to screw in a light bulb. And the answer is one, but it needs soft hands, and it needs very special control strategy. And here you can see the robot. Now note that the top and the bottom hands are grasping the two objects objects with very different poses. And so the question is, how might you figure out, or how should the robot figure out which is the correct approach and pose for grasping? This is super important in manipulation and in industrial automation. And here you can see how our robot is choosing two very different strategies. Again, a machine learning strategy that is trained on not too many objects, because we can kind of box all the different types of objects according to the enclosing box. So you don't need too many, given a certain fixed size for the manipulator. It can learn how to very intuitively and reliably reach for an object, no matter where the object is located. This is very different than what today's industrial automation does. So we can use advances in machine learning, and we can use new devices to improve how the machines reason about the world to get more flexibility. But now, as I said to you earlier, the machine can only do what the body enables it to do. And right now, the state of making new robots is similar to where we were in computing before we invented compilers. Every new robot is designed from scratch, very bottom up. It takes a long time to go through the process. So the question we ask is, can we bring computational tools to automate the design and fabrication of robots? And because this would allow the democratization of robots. So here's a user, let's call her Alice. We would like to give Alice the opportunity to automate many tasks in her home. So let's say Alice wants a robot to play with her cat while she's at work. Well, in this future, with stores named 24-hour robotics or 24-hour manufacturing, Alice could head to the store, could use an intuitive interface to design her robot. And when the design is fixed, the store can print the robot, and the cost will not be too high, and the cat will have a playmate. Okay, so how feasible is this idea? Well, it turns out that we can take natural language specifications for the function of machines, and we can parse those specifications to figure out what is the task the machine has to do, what kind of behaviors are needed for that task, and from that we can synthesize mechanisms that execute the task. And in other words, we can synthesize in a couple of hours a robot that will play chess with you. Now this robot, the brain of the robot was not done automatically, but the body was. The rough idea is as follows. There are many different ways to approach the problem, but you can start with a picture, any kind of image of an object. You can pass it through standard software to create a tessellation of that image that could then be unfolded in the way you see this Stanford robot bunny unfolded as a flat structure. And from that, you can automatically create a robot that would look like a bunny and that actually has built-in motion in the foldings that are comprising this robot's body. And you can imagine, you can take this idea and you can imagine applying it to every object in the world. For instance, we could apply it to the Sydney Opera House. And if the Sydney Opera House were a robot, this is what it would look like. Can we have sound, please? So we can take these ideas to turn ordinary objects into robots that could eventually make our lives better, and they could help us with physical work. Now, these ideas can be applied broadly at all kinds of scales. And an interesting application we've been thinking about is in surgery. Can we imagine a future of surgery that does not require incisions, that does not lead to infections nor to pain. And the problem that motivated our investigation is removing button batteries that are accidentally swallowed by people. And within 30 minutes, the button batteries would pierce a hole in your stomach tissue. So what we can do is we can take a robot, much like the bunny or the Sydney Opera House, miniaturize it, pack it into a pill-shaped iced encasing. And so the idea is that you could swallow this iced pill. When the pill gets to the stomach, the ice melts, and now the robot could be directed in the stomach to do useful things for you. For instance, here is a simulated example where the robot has a tiny battery in its body, tiny magnet in its body that can be used to pull out the battery. And later on, you might send another pill robot that has medicine embedded in its body and can go patch the wound and deliver medicine in a very precise way. We control these robots because we know where the magnet is, and so an MRI-like machine can be used to very precisely direct these robots. And by the way, this robot is made out of food, so you will be able to digest the robot. This robot is made out of sausage casing. So you can imagine using these ideas to create a future of medicine where for certain medical procedures, like removing foreign objects, collecting tissue samples, delivering medicine or patching wounds, there is no pain, no risk of infections, no incisions. So in the rest of my time, I want to tell you just a few words about how people who are not experts in robots might interact with machines. Now, we have seen a lot of activity in using natural language to control machines. You can speak to the machine responds to you. And the question we were interested in my group is, can you connect directly from your thinking, your thoughts, your brain activity to the machine? And right now we have very sparse sensors like these EEG sensors you see on the slide. There are 48 electrodes that measure brain activity, and it's really too sparse to make any sense out of what happens in your head. But there's one signal that this sensor can detect. The signal is something we all make very intuitively, very naturally, without training. And this is the signal we make when we see that something is wrong. So the "you are wrong" signal is called the error-related potential. It is localized and it has a unique profile. And with that, we can imagine a future of, could we get the video, please? We can imagine a future for manufacturing where people could observe robots from the distance, and I don't know why this is not playing. People observe the robots from the distance. If they notice that something is not right, they simply think, that's not right. And that signal can be detected in about 100 milliseconds and used to correct the robot's mistake. This can bring robots and people much closer to each other on the factory floor and change the future of industrial automation. So in this case, the robot is presented with paint cans and wire spools and has to sort them. And the robot randomly chooses to go one way or another. If the robot makes a mistake, the human thinks, that's wrong. And the robot then gets corrected. So in this case, look, the wire spool went in the wrong direction. The human had the thought that was wrong, and that was detected in 100 milliseconds. The robot corrected its mistake. So this is quite far out. It's not quite ready to be deployed, but it's a beginning for what the industrial automation might look like. And so industrial automation started with this amazing, beautiful robot called Unimate in 1961. And it's extraordinary to think that from 1961 to 2020, we are moving from one robot used in industrial automation to 31 million robots, which are projected to be with us by then. And these industrial robots are extraordinary. They do feats that humans can't even imagine doing. Yet they remain isolated from people on the factory floors because they're too heavy, too big, too dangerous to be around. And so a natural question is there better? And while we spent so many years thinking about industrial automation, and we have robots isolated from people, can we think about a future where robots and people work together? So look at this interaction between the child and the elephant, how delicate the elephant is with a trunk that could also be used to fend off a rival. Can we make robots that do the same sort of things? And the answer is yes. We're making advancements in material science, and through that we are able to make robots that are much softer, much more flexible than today's industrial robots. So, and this is our soft robotic fish that was able to swim side by side with physical fish in coral reefs. So what I would like to leave you with is the idea that we spent the last 60 years thinking about robots that are inspired by the human form, either manipulators or humanoids or robots on wheels. But robots could be anything. Robots could be made out of all types of materials, including food and fabric and plastics and paper. And so while I believe that the last 60 years of robotics have led to constrained, hard-bodied robots that are doing feats for industrial automation, the next 60 years will be about adaptive soft robots, pervasive robots that support humans in human-related tasks, in human-centered environments that will come in a diversity of forms and materials. Thank you.